Hello, everyone. This is the final type of reaction that we'll be discussing here in section 4.2 on classifying chemical reactions. That is the redox reaction. Your book is stating that the learning objective here is compute the oxidation states for elements and compounds. There's actually a little bit more to that. Your book actually goes a lot more detail than that. So what we're going to do is, in addition to that, then decide on which substance is oxidized and which substance is reduced. However, we will not get into balancing redox reactions, which is a lot more detailed. That is something we will save until next semester for those of you who will be going on to take Chemistry 1B. So let's find this section in your textbook and discuss it. Okay, so we're going to talk about oxidation reduction reactions. This is a specific type of reaction that is often very important in chemistry, and it's defined by the transfer of an electron, or transfer of one or more electron. The term oxidation is a little bit of a misnomer because we've expanded the definition. It was initially just involving oxygen. However, it does not have to involve oxygen in order to be an oxidation reduction reaction. So this is the definitions we'll be using for oxidation and reduction in this course. Oxidation is defined as the loss of electrons. Reduction is involved as the gain of electrons. Now this might seem a little bit counterintuitive at first because we have the word reduction and the word gain kind of together. However, there is something we'll be doing with this that will help it make a bit more sense as we get into oxidation numbers. But essentially, you'll have to sort of memorize that which goes with which. So oxidation is loss of electrons, reduction is gain of electrons. If you Google, you can find a few mnemonic devices to help you with that if that is something that works for you. Otherwise, just sort of kind of remember which is which. We also can talk about reducing agents and oxidizing agents. And the idea here is when we say it's an agent, it means we're trying to use it to do something to something else. So the reducing agent is oxidized, the oxidizing agent is reduced. Again, the idea here is that these two always go together. If something is losing electrons, they have to go to something that's gaining electrons. They don't just vanish. So if something's a reducing agent, by being oxidized, it's causing something else to be reduced. So there are chemicals that are specifically used for the purpose of causing something else to be either oxidized or reduced. And that's why we use this term to describe those sorts of things. Okay, so we're looking at the transfer of electrons. Up here we're showing half reactions as a way of showing that. And that's really a good way to show that, so we can see we're losing the electrons here, and we're gaining the electrons here. The half reaction is something we'll look at in more detail in the second semester in Chemistry 1B if you go on to take that course. Okay, so what we'll be looking at for this course is how to know if something is oxidized or reduced. And to do that, we use oxidation numbers or oxidation states to help us make that decision. These are similar to ionic charges, and if we have an ionic charge, it will be the same. However, there are cases where you do not have an ionic charge where the use of oxidation numbers is also important. So we're going to go through a series of guidelines for determining the oxidation state of elements that are participating in a chemical reaction. You'll notice I said elements, so we're assigning the elements things. When we have a compound, we have to look at each element within the compound. So the first one is that if you have an atom in its elemental state, it is always 0. So anything by itself essentially will have an oxidation number of 0. So here in this reaction up here, hydrogen is by itself, it's 0. Chlorine is by itself, it is 0. Okay, those are their initial oxidation states. If you have an ion, so we're saying monatomic ion here, then its oxidation number will be the same as its charge. Okay, so let's scroll up a little bit to our example up here. So here, for example, sodium has a +1 charge. It would have an oxidation state of +1. Chloride down here has a -1 charge. It would have an oxidation state of -1. And then some common nonmetals will often have somewhat predictable oxidation numbers. And this is going into more detail than we need to, so we'll just focus on some of the more important ones here. So hydrogen is +1 if combined with a nonmetal, and -1 when combined with a metal. Okay, so hydrogen will kind of act differently than pretty much any other element in that way, in that it can be a +1 with a nonmetal, -1 with a metal. So up here, we would say that it would have a +1 because it's with a nonmetal. So that's how we would do that. For oxygen, what I'm going to say here, don't memorize all of these possibilities, but just notice that it's -2 most of the time. So oxygen is -2 most of the time. Exceptions could happen with hydrogen and with fluorine, but because of the way your textbook has it laid out, we'll just limit that to exceptions with hydrogen. You might at some point see a molecule in this class where the question is not about oxidation number, but you end up with, if you wanted to look at it, you would end up with something else for oxygen. So be aware there are other possibilities, but in terms of assigning oxidation numbers in this class, basically oxygen will be -2. And then the halogens are usually -1. That is always true for fluorine. The other halogens will often be something other than -1, or I should say they can be something other than -1, particularly if they are with an oxygen. And I don't know that we have examples of that readily available here, but with the chlorate ion, for example, or anything that you have an oxyanion, the oxygen is what's determining the overall oxidation numbers there, not anything other than the oxygen. So typically halogens are -1. And then the fourth one is where we kind of bring it all together. The oxidation numbers of all of the atoms within a substance have to be the charge on that substance. So if you have a neutral compound, like up here we have HCl, everything adds up to 0. If you have an ion, and we don't have any examples here of polyatomic ions, but if you do, so down here is an example of a polyatomic ion, it would have to add up to the charge of the whole ion. So everything here adds up to a -2. So this fourth rule, how we use the fourth rule is we use the things in here as, okay, we know what these are, and then whatever else you have, we know what it adds up to, and then from there we figure out the other parts of that. And that's how we assign oxidation numbers. So I want to look at some examples of that down here. And I think we'll look at, again, just one example, and you can look at the others on your own. So the first example is H2S. So from our guidelines up here, we had hydrogen. We didn't have sulfur in here anywhere. We just had hydrogen +1 with nonmetals. So sulfur is a nonmetal. So we would know hydrogen is a +1, and we have 2 of them. We also know that the total thing has to add up to 0 because this is not an ion. There's no charge here. So everything adds up to 0. Hydrogen is a +1. So we have 2 hydrogens, so 2 times 1, and then we have sulfur. We have 1 of those, so 1 sulfur 2 hydrogens add up to 0. So if we do the kind of the algebra here, we see that the sulfur has to be a -2 to basically balance 2 plus 1s for the hydrogen. Okay, so those would be the oxidation numbers we would assign there: -2 for sulfur, +1 for hydrogen. And then you could do similar things for these ones. And I'll just give you a few hints. So again, it has to add up to not 0 here, but the charge when you look at B. And then for C, you have, 3 things here. What I would suggest there is, if you look at that as a monatomic ion for the sodium, so what charge would the sodium have by itself? And then from there, figure out the rest using the other guidelines we looked at. So I'll let you do some additional examples there. Okay, so it is important to assign oxidation numbers. Actually, before we move on, please pause and go through, do some examples. Make sure you're comfortable assigning oxidation numbers before we get into this next part, because assigning oxidation numbers is sort of the baseline for the next section, and that next part of this section, I should say, in that you have to have correctly assigned oxidation numbers in order to make the decisions that we'll be looking at going forward. So when we are assigning oxidation numbers, we can look for changes in oxidation numbers as evidence of a redox reaction. So if the oxidation number is increasing, and when I say increasing, what we're talking about is from one side of the reaction, from reactant side to product side. If it increases, there's an oxidation. If it's decreasing, that's where we have the reduction, again, from reactant side to product side, if it is decreasing. So I think we have some examples here. So the examples we'll look at are some specific types. Let's actually go back up here, and then we'll come down and look at some of the additional. I want to start with a fairly simple example. So here we can assign oxidation numbers. So we know hydrogen is 0, chlorine is 0 because they're by themselves. Over here we know hydrogen will be a +1 with a nonmetal. Because the whole thing has to be 0, then the chlorine is a -1. So we can look at how they change. So going from here to here, we go from 0 to +1. So hydrogen goes from 0 here to +1 over here. So it went up. Okay, hydrogen increased its oxidation number. Okay, so that is an oxidation. So we can say hydrogen is oxidized here. Chlorine goes from a 0 here to a -1 over here. So the oxidation number is going down. So that's a reduction. So we could say chlorine is reduced. Hydrogen is oxidized and chlorine is reduced. Okay, so that's how we use the assigned oxidation numbers to determine what's being oxidized and what's being reduced. A couple of examples of important redox reactions. One is a combustion reaction, and this will often involve oxygen, and you are reacting in a way that produces a lot of energy. We'll talk about energy in a later chapter, but here's an example of a fairly complicated combustion reaction. And in this particular case, you're not using oxygen, but this would be a big one to balance. We're not going to go through balancing that, or balancing, I should say, also assigning oxidation numbers for something quite that involved. Other typical redox reactions that are important are often called the single displacement reactions. In these reactions, you have something that is initially by itself that then becomes part of a compound, and in so doing, part of what was initially in that compound basically gets kicked out of the compound, is then by itself. So this is a type of redox reaction called a single displacement reaction. And it's often fairly straightforward to decide what's being oxidized or reduced in a single displacement reaction. So let's go ahead and take a look at that. So here we have, often we'll have one of the things by itself is a metal, and so it will start with an oxidation number of 0, and then when it is paired up, it will have a positive charge, will have a positive charge, and thus will have a positive oxidation state. So in this case, we have a +2. We can see how the charges would balance there. And we're going from 0 to +2, so that's an oxidation. So if you have a metal by itself as the reactant in a redox reaction, then that metal is being oxidized. And then when that happens, whatever ends up by itself is then being reduced. So we can see that as well. So here we have hydrogen with a nonmetal, so that's a +1. So we go from a +1 to a 0. So that's a reduction from +1 to 0. Similarly here, the metal that starts out by itself goes from a 0 to a positive. So that's an oxidation. And then the number that starts out initially in a compound goes from that to by itself. So that is a reduction. Okay. So whatever metal is starting out initially by itself is going to be oxidized from when we get to the product side, and then whatever is initially in a compound is then going to be reduced. Okay, so that's one way when you have a single displacement reaction to kind of quickly make those sorts of decisions. And let's see, here you can decide, this is an example of deciding if it is a redox or not, so you can assign oxidation numbers to make that decision, and it kind of walks you through the steps there. I wanted to end by just reiterating that we are not doing this. We are not balancing redox reactions until next semester. So that is it for this part of the section on balancing redox reaction.